All right, let's look at the proof of power rule for derivative, just for the simple case anyway. All right, so before we get into the proof, I'd like to look at something called Pascal's triangle. All right, this is pretty interesting. All right, let's say you have a quantity x plus h to the 0th power. You get 1, so we get 1 here. All right, and to the first power, you have x plus h, but we're going to pay attention to the coefficient of each term. So it's going to be 1x plus 1h, right? If it's squared, you have x squared plus 2xh plus h squared, so coefficient would be 1 and 2 and 1, right? And if it's cubed, it's going to be 1 x cubed plus 3x squared h plus 3xh squared, and then 1h cubed, right? And the fourth one, this is going to be the last one. So you have a 1x to the 4th and a 4x cubed h plus 6x squared h squared, 4xh cubed, and a 1 h to the 4th. All right, so if you just pay attention to those coefficients here, it forms a triangle. This is called the Pascal's triangle. And we can easily continue building, more layers of Pascal's triangle. All right, so here's what we need to notice here. All right, so you can see that the beginning and the ending is always 1. All right, so you can see that you have all 1s here and you have all 1s here. Right, the middle number is determined by adding the above 2. So for example, 2 is 1 plus 1. All right, 3 is 1 plus 2. Right, 4 is 1 plus 3, and 6 is 3 plus 3. Right, so if you were to do the next one, so maybe I'll erase this dot 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 here. So if you were to do the next one, so which is x plus h to the 5th power, this is going to be, right, so we know that it's going to start with 1, right? Then you're going to add those guys up. So it's going to be 5 here. That's going to be 10 here. That's going to be another 10 here. That's going to be 5 there. And we know that the last one is 1, right? Then you can see that x is starting from the largest power and they go down 1 by 1. So this is going to be largest power would be x to the 5th. And then this is going to be x to the 4th, x to the 3rd, and x squared, and then you have x, right? H is starting from 0 to, h to the 0th power, 1st power, 2nd power. So this is going to be just that. Then this is going to be h plus, sorry, it's kind of messy, h squared plus h cubed plus and h to the 4th plus h to the 5th, right? So you can build, more layers this way. All right, but anyway, so what you really need to notice is this. So in general, right, we don't need a lot of these coefficients, just maybe the first two. So here, x plus h. So if it's to the kind of a general nth power, and what would you put? All right, so just the first two, maybe the very last one, right? We know that the first one is going to be x to the n. So it's going to be 1 x to the n, right? Next number is, the second number is always the same as the power, right? 4 is 4. If it's cubed, it's 3. So this is going to be n times x to the n minus 1. Then you have h, right? And I don't really care what goes on in between. And the last one is obviously 1 h to the nth power. All right, so this is quite useful in proving the power rule, so let's keep this in mind. All right, so let's use that to prove the power rule. All right, so we want to find the derivative of x to the n. All right, so using the definition, so it's going to be a limit as h approaches 0. All right, so you have x plus h to the n minus x to the n all over h, right? So I'm just following the definition. So this is the derivative, right? All right, then we're going to use this Pascal's triangle trick to expand, right? So we're assuming that n is a natural number, but the power rule works with any real number. All right, so we have that, and I guess here, if you use the Pascal triangle, we know that this is going to expand to, so first term is x to the n. Next term is n times x to the n minus 1 h. Then we say dot, dot, dot. And the last one is h to the nth power. All right, so that's the expansion of x plus h to the n. And then you're subtracting x to the n, and then you have all over h. All right, then what you're gonna do is this. We're gonna just try to cancel out as much as possible, so you have x to the n and x to the n cancel out. All right, and the great thing about this is going to be all the remaining term on top have h in it, so I'm gonna pull h out. So you have a limit as h approaches 0. All right, so I'm going to pull h out from the first term. So you have n x to the n minus 1 and plus. All right, next term is going to be, maybe I should, so I don't even know what number, what coefficient goes here. Actually, I know, but I don't need to know. All right, so the next term would be x to the n minus 2, then h squared. But one of the h's pulled out, so you're going to have h here. And so on. So all these remaining term is going to have h in it. So last one is h to the n minus 1, because one of the h is pulled out, all over h. All right, so we can cancel h on top and h on the bottom, common factor. All right, now h is going to 0. All right, so you can see that all these remaining terms, except for the very first one, has a factor h in it. So as h goes to 0, all these terms, right? So starting from the second term on, they're all going to 0 because it's multiplying by 0. H is going to 0, right? So only thing that's left is n times x to the n minus 1, right? So this is just a special case. This doesn't prove the case where n is a non-natural number, but n is a natural number. We can prove this, right? So here, that proves this power rule, right? For a simple case when n is a natural number. All right, that's it. I hope that this was clear.